Welcome. Today we're going to be taking a look at the lesson entitled Trigonometric Equations Conditional Day 2. And so this would represent a continuation and extension of what we looked at yesterday, solving trigonometric equations where we're trying to find the value or values of the variable that make the equation true. And so what we'll do is rehash a few ideas from yesterday and then obviously extend on that to a different type of problem as well. So let's start example 1 at the top here. This would be kind of at the upper echelon of what we did yesterday there. I've got a variety of things going on, and what we're going to do is solve this particular equation on our primary interval. So if you remember what we talked about yesterday, there are an infinite number of solutions to this equation right here. What we're going to do is just find the solutions on this interval right here, starting at 0 and all the way up to, but not including 2 pi. So let's give it a try. I see a very similar situation to yesterday in that it has that nice quadratic trinomial feel to it. So what you would want to do, and actually don't do this on your paper just yet, but basically what we would think to do is something like this. Try to get it in factored form set to 0. The problem, of course, here, as I look at this problem, is that I have sine as the quadratic term and cosine as the linear term. So if I was to try to factor this, try to just kind of think, and don't, again, write anything on your paper just yet, but if I was to do something like that to get 4 sine squared of x, well, my outsides and insides, I'm hoping you would all see, would combine to a sine of x, not a cosine of x. And so I would argue that the way it is right now is probably not going to work out for us in terms of factoring. So we need an alternative. And I think, again, as I believe I've implied, we have a dilemma with the two different trig functions. So the question is, can I get it into a single uniform trig function moving forward? Then I can factor it. I don't see a way around factoring with this here and this here. So what do you think we're going to do? Do you think we're going to change the sine squared and put it in terms of cosine? Or do you think we're going to take the cosine and put it in terms of sine? Well, if you remember correctly, the great connection between the two major functions is on the squareds. And so the way I see it, everybody, and you can either back me up on this or find a different approach, but essentially we know that sine squared is 1 minus cosine squared. So we talked about the prospect of using identities to replace a particular part of the equation. And in this case, that's exactly what I'm going to do. I'm going to take sine squared and replace it with 1 minus cosine squared. Now I have a quadratic term. It just happens to be in cosine, which probably is what is going to allow us to go forward. Okay. Well, now it is really, for the most part, all algebra from here. So let's simplify. Let's work on it together. Work a half a step ahead or a half a step behind, your call. But let's distribute. I'll try to take every step for you so you can kind of see what I'm doing here. But basically, I would go ahead and do that. I would probably combine the like terms. Here's the 4 and minus 5. Let's clean this up a touch. So I have this, and then this. 4 minus 5 gives me that. Okay, so far, now again, it has that great quadratic feel to it, where I am going to factor with the two binomials. I would do maybe one more thing. This is just me personally. I'm not a big fan of having the negative outside in front of the quadratic, and if I can avoid that, I try to. So I'm going to divide everything by -1, and being an equation, I can do that because as you can see, I am going to still balance it out over here. So just going to change the signs here. 4 cosine squared minus 4 cosine, and then how about a +1? And that's looking great. And that it's a good position to be in, because it allows us to take the opportunity and try to factor at this stage. And so let's do that together, everyone. So I'm seeing this. Now I get my binomials like I tried to do at the very beginning, but now I think I'll have some more success with it. And let's see what we get. I'm going to try the 2 cosine and 2 cosine. So that should give us 4 cosine squared. Looks like I have to multiply to 1 on the back, so certainly a 1 and a 1. And multiply to a positive, combine to a negative there. So I'm thinking it's got to be minus minus. And then I just do a quick check on the outside and inside. Outside, inside, and looks good. Combines to -4 cosine of x. Excellent. And as a matter of fact, this is kind of nice because obviously we would set both factors to 0. And so let's do that together here. And you can almost see when I start to get this together a little bit here, I get cosine of x equals 1/2 on this end. And I also do this exact same thing over here, and I get cosine of x equals 1/2 on this end. So as a matter of fact, as you saw, we end up getting the same factor twice. So whatever works here is obviously going to work here too. So you know, you can dot, dot, dot this or even cross it out. We don't need to kind of deal with that because, of course, everybody, I'm just dealing with it right here. All right. Well, if you remember, this is one of our great unit circle ratios. And so the question, of course, becomes, what angles between 0 and 2 pi have a cosine ratio of positive 1/2? I'm going to draw my unit circle just to get that perspective taken care of. And I would encourage you, either you have your unit circle in front of you or you just know your unit circle, but should know this piece right here. So let's kind of talk about this. Where is cosine positive? Cosine is positive in quadrant 1 and quadrant 4. And if I get the cosine ratio of 1/2, that would be up here and down here, give or take. So I'm hoping everybody would realize from there to there is going to be pi over 3. Cosine of pi over 3, of course, is 1/2. And then working my way around from here to here, and it looks like that measurement would be 5 pi over 3. And we all know, of course, the cosine of 5 pi over 3 is also 1/2. All right, I'm going to box that up. That's looking really nice. If I wanted to go further, if I was to ask you for all of the solutions to this equation, remember you would say, well, I've got one at pi over 3, and then it repeats every 2 pi before and after that. So we would say pi over 3 plus 2 pi k. And in this one here, I have one at 5 pi over 3, and in every rotation around again, I would get another solution. So 5 pi over 3 plus 2 pi k. And as I said, on this particular problem, I just asked for between 0 and 2 pi. Okay, so a good practice problem from yesterday. Did want to make that connection before moving forward. All righty. Now for the next step. What happens when we see ratios that are not those perfect, nice ratios that we've been exploring all semester long? So in this case, I would be looking for the angles that have a cosine ratio of 0.45. Well, that's not one that we explored, but there are angles that have a cosine ratio of 0.45. We're just going to need the calculator to give us some assistance on that. So let's just answer the prompted questions here and maybe take sort of a visual approach to this, and then we'll start to move forward. First and foremost, I guess letters A and B go together. It does say how many solutions are there on the interval between 0 and 2 pi. So I'll tell you what, why don't we draw our unit circle. I've always thought of the unit circle as sort of the best visual tool for a variety of topics that we're working on in this semester. So I'm going to go ahead and see that piece right there. And then remember what we're going to do, everyone. We're going to start here, and we're going to go once around the unit circle, so from 0 to 2 pi. And in how many different places am I going to get a cosine ratio of 0.45? So remember what that means, everybody, first and foremost. On the unit circle, and just on the unit circle only, what that means is that I would have an x value of 0.45. So here's 0, here's an x value of 1, 0.45, I'll just sort of put right in here. Hopefully everyone's okay with that piece. Now, where would we get a cosine ratio of 0.45 as I go around? Well, I would probably get one up here somewhere. Does everyone kind of see that? So going up right here somewhere. Sounds good. And then I keep going. Where am I getting that exact same x value of 0.45? Probably also down here. So I think one of our solutions will be from here to here. And then another one of our solutions will be from here to here. Hopefully everyone's okay with that premise. All right, so one solution up here in quadrant 1, one solution here in quadrant 4. Okay, so how many solutions are there on this interval? Absolutely, there are 2. And we've been seeing that now over the last lesson or so. Okay, which quadrants do the solutions lie in? Well, we of course know that cosine is positive up in quadrant 1, and cosine is also positive down in quadrant 4. So 1 and 4. Now here is sort of the drawback, the limitations to our taking an inverse, because that's how we're going to have to deal with it. I'm going to grab my calculator momentarily and do this. But what we would want to do now is just good algebra. We would undo cosine by taking the inverse cosine of both sides and getting the variable by itself. Of course, the problem lies in the way that inverses are defined. And so that is the trick. That's what we're going to have to work our way around today. So first and foremost, everyone pick up the calculator if you would. And let's go to radian mode. Okay, I'm in radian mode. And now I'm just going to type in inverse cosine 0.45. So remember, you're asking for the calculator for the angle measure in radians that has a cosine ratio of 0.45. All right, and I get something like that right there. And that's pretty much what I'm going to use. Let's see, let me see where I can write it in here. So here's what I have, everyone. When I did the inverse cosine of 0.45, I got this number right here, about 1.1040, give or take. All right, now, as a matter of fact, what you just got from the calculator was the rotation around on the unit circle from here to here. Or, if you want to now expand it, it's the angle that has an x to r ratio of 0.45. So don't write this on your paper, just kind of thinking out loud here. So here's the angle right up here. That would be about 1.1040 radians. And basically that would have a cosine ratio of 0.45. So an x to r ratio of 0.45. That's the angle that produces it. But notice, as I said, the limitations on taking an inverse cosine. Can the calculator simultaneously give you both answers? No. It gave us this one, but now we have to find a way, everybody, to get this one. And the way we're going to do this, the way we're going to kind of set it up here, everyone, is by using reference angles and their rules. So I'm going to write just like this for right now. We're going to use the reference angle rules. In this case, the two quadrants were 1 and 4, and so that's what we would use them for. So we got this one, as a matter of fact. And by the way, the reference angle, so to speak, is what the calculator gave you. And as a matter of fact, that is one of the answers. But we would need the reference angle to give us the other one down here. And that's what we're going to have to work around. Okay, so it's going to take a little time and a little patience with this. I've laid out some strategies and a fairly rigid process to go through it. So if we kind of follow that step by step, I think we'll have some pretty good success with this. So let's see if I can explain it to you as best as possible. All right, the next thing on your paper, it just says necessary information for solving equations with approximations. So this is where we don't have those perfect, exact unit circle ratios, the 1/2s, the √2/2s, the √3/2s. Obviously, there are an infinite number of ratios out there. And so what happens if we can't get them to be our exact answers from our unit circle? Well, again, we need the calculator to sort of help us along. So these are the 3 things that I narrowed it down to, 3 things that we've developed that you really do need to know quite well. So first of all, you definitely have to know where things are positive and negative. So just to rehash this, remember in quadrant 1, they're all positive. In quadrant 2, sine is the one that's positive. In quadrant 3, tangent is the one that's positive. And in quadrant 4, of course, cosine is the one that's positive. So like on that last one, we had a positive cosine ratio, so I knew it had to be in quadrant 1 and quadrant 4. So you need to know where things are positive and negative. Okay, this one's not all that necessary. I put it on your sheet because we are going to be taking inverses, and they can be very tricky. We're going to really have to work around that. And so I guess we should just understand what the calculator is telling us. That's the key. So here's what I just did on my paper, just in terms of when you do an inverse sine and an inverse cosine and an inverse tangent, remember there are defined intervals for your answer. And so you really kind of just need to know that these are the values that the calculator is going to give you. So what I mean by that is when you do an inverse sine, you know that you're going to get an answer somewhere in between -pi/2 and pi/2. So if you're looking for an answer in quadrant 2, the calculator is not designed to give you that when you do an inverse sine. So we're going to have to find a way around that. Same with cosine, the interval is from 0 to pi. When you do an inverse cosine on your calculator, it is programmed only to give you numbers in between 0 and pi. So for example, like this last one, how would I get an answer in quadrant 4 if the calculator is only giving me these pieces right here? And in tangent, not that we're going to do a ton with tangent, but if you remember, tangent had basically the same interval as sine. Not exact, but basically. Okay. Now this is the key, because as I said, we're going to be using reference angles here. So please put an asterisk, if you would, next to that piece. And you have to know the reference angle rules for each quadrant. Now we took some time and developed this when we did reference angles. So if you're not sure where they came from, please go back and take a look at your notes from reference angles, and you'll see pretty much exactly this piece. So I guess the prospect here is going to be, if I have the reference angle, how can I get the true angle measure? So if I know my reference angle, what we're going to call as x prime, how can I get the angle in quadrant 4 that meets it? And same in quadrant 3, same in quadrant 2, etc., etc. So these were the rules that we applied way back when. The good news for a quadrant 1 angle, and you'll always hope that one of your answers is in quadrant 1, is whatever you do get from the calculator, this reference angle, that is going to be your answer. The reference angle and the true angle are the same. Now quadrant 2, it's a little different. If you remember, again, we're radians here, so I'm going to go pi. If this was degrees, we would be talking about 180 degrees. But basically, it would be pi minus the reference angle. So when that calculator spits out the reference angle, and that's what we're going to want it to do, we do pi minus. That's our answer in quadrant 2. Quadrant 2 is pi minus. Everybody, in quadrant 3, it's pi plus. Same deal, everybody. When the calculator gives us the reference angle, and I know my answer is in quadrant 3, I do pi plus, and that's one of my answers. And then last but not least, quadrant 4, this is what we did way back when. And as a matter of fact, if you remember just the investigation we did a few minutes ago, that's what I would have done to my answer from the calculator. If I wanted to, the cosine of x equals 0.45, if you remember that one just from above, if I wanted that quadrant 4 angle, all I would have to do is take 2 pi minus this. And that would have given me the other one. And so, I'm sorry, I'm going to go back aboard for just a second. See that answer, that 1.1040? If I do 2 pi minus that number, guess what? That puts me right here. Because the reference angle is right here, and so as a result, there it is. Okay, so that's what we're going to be doing. Cool. All right, so as I said, it's a fairly rigid process, so I'll try to be as clear as I can here, especially when we do the examples. I'll lay it out 1, 2, 3. This is what we're doing, and hopefully it'll work. So anyway, here it goes. Strategies for solving equations with approximations. Number 1, we have to take an inverse. And what I'm going to ask you to do is take the inverse always of the absolute value of our ratio. So we're going to try to make it positive no matter what. Because if you remember correctly, reference angles are always positive and acute. And so by doing this, it sort of allows us to streamline it a little bit, I believe. So step number 1, find the reference angle. We're going to call that x prime. Then step 2 is to go back and look and see which quadrants our actual angles are going to be in, our solutions are going to be in. So we've got to talk quadrants, where things are positive and negative. And then after that, everybody, what we're going to do is just pretty much solve. We're going to use our quadrant rules for the angle and solve for the variable. Now again, I know that just looks like a whole bunch of verbal jargon at this point, and you're not sure what necessarily is going on. Don't worry about it. We're going to lay it out here with a couple examples and try to really put it into context. It looks like I have a little asterisk here. Just wanted to rehash one thing. And so here's what I would say. Unless the values are at a max or a min, you can kind of think of that sinusoidal wave, unless we're at a max and a min, and this is the key, everyone, and I hope you've been seeing this now for the last day and a half or so, but there are, oops, I missed a word there. There are 2 solutions per cycle. So hang on one sec, 2 solutions per cycle. So maybe the calculator at most will give us 1. We have to find a way to get the other one. Because if you think about your nice sinusoidal curve, something like that right there, very simply, if I want to know the solutions, I'm going to get 1 on the way up, 1 on the way down. 2 solutions per cycle, something like that would do. Unless you're at a max or a min, that's the only time you get 1 solution in that cycle. Okay, so that's what we're going to be working around there. And so, hey, it's just, we're going to go one at a time here. I have a relatively easy one to kind of start us out. And again, I'll try to be as clear as possible with the 3 steps that I wrote above. So you see on your paper 3 strategies there. What I will try to do is say, okay, this is what I mean by number 1, this is what I mean by number 2, and this is what I mean by number 3. So let's try it. The example 2. 3 sine of x minus 2 equals 11 sine of x minus 1. There are an infinite number of solutions to this equation. I would like the primary 2, most likely here, the primary 2 on our primary interval, of course. So that would be from 0 to 2 pi. So this is just a basic algebra 1 problem, except instead of x, it's sine of x. But I'm going to treat it the same way, everybody. I'm going to subtract 3 sine of x and bring that over. I hope everyone's okay with that piece. So I'm going to take this term right here and just combine it over here on this side. I hope you're all right with that. Just good algebra. Nothing more just yet. Next piece, everyone, I'm going to add the 1, so I get that right there. Okay, now we're rolling. I'm going to go ahead and divide by 8, everybody. So sine of x, and I'm going to leave it like this for just a moment. So sine of x equals negative 1/8. Now, up until this point of time, we would start asking ourselves, and we're going to still ask ourselves the same question, but what angles have a sine ratio of negative 1/8? Well, this isn't one of those great ratios that we've been memorizing, so to speak, over the semester, but there are a couple angles that have a sine ratio of negative 1/8. So even though I don't know those off the top of my head from studying the unit circle, I know that there are a couple answers. And so what we're going to have to do is kind of figure this out here and go for it. So what angles have a sine ratio of negative 1/8? All right, so here's what I do, at least initially. I'm going to put a number 1 here, and the first order of business is to find the reference angle. So I'm going to write this, find x prime. And to find x prime, remember what a reference angle always is, everybody. It is always acute, and it's always positive. So what I'm going to do here is a little unorthodox, but for right now, everyone, I'm going to take the inverse sine of positive 1/8. Okay, because that's going to give me a positive ratio and acute. If I take the inverse sine of negative 1/8, unfortunately, it's going to give me a negative value for x prime. Now, we could probably interpret what that means, but I think this is just a little cleaner, in my opinion. So what we're going to do is find x prime. That's why no matter what this, for just a moment, temporarily, we're going to take the inverse of the positive ratio to get x prime. Okay, so let's do that. I'm going to bring up my calculator right here, and I'm going to do inverse sine 1 divided by 8, and I get that right there, 0.1523. So everybody, on your paper, if you would, x prime equals 0.1523. Okay, now I didn't mean to throw you off by changing that sign, so let me try to be very clear on that piece. That was a quick temporary step, nothing more. Just to get the reference angle, which is acute and is positive. That makes the next couple steps pretty easy to work with. So, number 2 is to go back, and here's the equation, everybody. I'm going to just do this. I don't want to box it up as it's an answer, but I do want to focus on that piece. Remember what I am trying to solve for. I am trying to find the angle measures that have a sine ratio of -1/8. Okay, everyone, so now I need to know my unit circle, of course. And where is sine negative? So sine is negative in quadrants 3 and 4. And so as a result, if I'm going to solve this particular equation, I know one of my answers is somewhere down here in quadrant 3, and one of my answers is somewhere over here in quadrant 4. Okay, I hope everyone's okay with that. As I rotate around once around my circle, okay, one answer here in quadrant 3, one answer here in quadrant 4. Okay. So that is step 2, finding out where we're going to get our answers. Here, sine negative, 3 and 4. Okay. Now the last step. And it says, very simply, set up your quadrant rules to solve. Because remember, of course, this is not one of our answers. If I take the sine of this angle right here, I'm not going to get 1/8. I'm not going to get -1/8. So what I have to do is use this in order to get the ones where I would get -1/8. And that's based on the quadrant rule. So quadrant 3 says very simply, to get your variable, to get the thing that's missing, this right here, I do pi plus the reference angle. I'm going to do it completely right there. So pi plus. And so this would be pi plus 0.1253. Okay, we're going to get that momentarily. And by the way, that is one of our answers. And then over in quadrant 4, if you look at the front side of the paper, quadrant 4 basically says, you know what, to get that angle, the one in quadrant 4, because the calculator wasn't able to give it to us, we're going to use the reference angle that the calculator gave us and take it away from 2 pi. And oops, let me do one thing first there. Sorry, again, do want to be totally consistent with you on how I write things. So minus x prime, and so x equals 2 pi minus 0.1253. Now you would grab your calculator at this stage and actually get these values. I happen to have a couple here. I'm going to ask us to go to about 4 decimal places for these, just for right now. So that would be one answer. And this would be the other answer. If I do 2 pi minus 6.1579. I'm going to box that up. And let's take a look at that graphically for just a second. And then we'll pick up the calculator and see it as well. So picture, if you would, about 3.27 radians, somewhere in there. That would be right about here, just past pi. Does that look like it would have a sine ratio, or on your unit circle, a y value of about -1/8? Yeah, it does to me. And then the other one there, about 6.15 and change, that would be on the other side. It's perfectly symmetrical. Of course, that would be this one right here. Does that look like it has a sine ratio of going down about -1/8? Absolutely. So one of our answers was from here to here. The other answer was from here to here. And there are your two. Let's confirm. So -1/8, by the way, happens to be about -0.125. So theoretically, this angle should give us that sine ratio, and this angle, should give us that sine ratio. So let's do it. So everyone, I'm going to type in our answers. It's a good way to just see if we're on target with this. So 3.2669. Do I get about -0.125? Yeah, again, we rounded there, so it's not going to be perfect, but that seems to be 1. There it is, negative, and this is about 1/8. Let's try the other one. Sine of, I've got 6.1579. And same thing, as you can see. Again, pretty much right on target. There's -1/8. So I would go back and just check your answers after you get them. Make sure. All right, let's just quickly recap the 3 steps, and then we'll do the last one of the day. Number 1, find the reference angle. Always acute, always positive. Then go back and figure out, okay, how am I going to solve my equation? Sine is negative in these 2 quadrants. So we use our reference angle and the rule in that quadrant to solve for the variable. That's how it's going to work, everybody. So let's just try one more. Ooh, really hard one. should look familiar to the first one we started with, by the way. So sine squared and cosine of x. Not good. So I'm going to go ahead and take a couple steps myself here to just get the ball rolling, just like we saw last time around. So now this is the second time. I think we do want to use an identity. It has that quadratic feel, that quadratic trinomial, but the only way to factor a quadratic trinomial that's in trig form is to make sure they're in the same trig function. So I'm going to do the same thing here, everyone, just good algebra. Okay. And then let's combine like terms. So I have this. And 8 minus 5 should give us 3. Looking good. Just so happens the same thing works out this time. I'm not a big fan of the negative out in front. So I'm going to go ahead and divide by -1 there and get 8 cosine squared of x. How about plus 10 cosine of x minus 3 equals 0. Now it has that great quadratic trinomial look to it, where I should be able to find two factors and set them to 0. All right. Now, it'd be great for you to take a moment, maybe pause the video here, and see if you can come up with our two values, or I should say our two factors. And so come on back for a second and see how you did. Well, I did this. I got 2 cosine of x plus 3 when I factored this myself, and then 4 cosine of x minus 1. If you're still having some issues with factoring, let me know, and I can definitely help you with that. But should be okay with that piece. All right, so now what we do is we set each factor to 0. So let's do that together, everyone. And I get cosine of x equals -3/2. And everyone, I get cosine of x equals 1/4. Now, just to get this sort of moving forward, I hope everyone's okay with what we have so far. Here's where we kind of pause for a second and we figure how we're going to move forward. Now, I will tell you straight up here, this is going to be good news, bad news in terms of the amount of work we're going to have for this. Officially, I would have to do it for both of these. I would have to solve this equation and solve this equation. Neither of these are obviously ratios from our unit circle, so we would have to perform the same steps. But as I said, there is some good news with this, and I'm curious if you see something here with these ratios. Here, I'm looking for a cosine, or I'm looking for the angles that have a cosine ratio of -1.5. Here, I'm looking for angles that have a cosine ratio of +1/4. Okay, I'm wondering if anyone saw it. Look at this one, everybody. Can you ever have a cosine ratio below -1? And so even if I try to solve this through my wonderful rules here, my rules of thumb, this simply doesn't work. I can't find any angles that have a cosine ratio of -3/2 outside of our interval. But this one, we're going to go ahead and solve. So I'm going to come right up here now, and let's go for it. So cosine of x equals 1/4. I'm going to do this. I kind of did this last time. That's a good stop to pause, breathe, and see what we're going to do. So now, everybody, it's the 3-step process. Number 1 is find the reference angle. So find x prime. And so what I'm going to do is take the inverse of +1/4. It's positive anyway. But no matter what, I always try to make this ratio positive in order to get x prime. So I'm going to take inverse cosine of 1/4 and get x prime. So everybody, you do the same. So step 1 is you have to find x prime. So inverse cosine, 1 divided by 4. So what angle up in the first quadrant, that's what it's giving us, has a cosine ratio of 0.25. And I get about 1.3181. Okay? So first order of business is to get x prime, acute and positive. And that number is definitely acute and positive. Okay, good. Now, step 2. Everybody, go back to that equation that we kind of boxed up here and remember what it's asking. We need the angles that have a cosine ratio of positive 1/4. So think about it for a second, just in general terms. Where are we going to get a cosine ratio of positive 1/4? Well, cosine is positive up in quadrant 1. Cosine is positive down in quadrant 4. So 1 and 4. Just set those up side by side. And now, everybody, we undo the cosine part to this, but it's not so straightforward as just undoing with an inverse and getting your answer. What we want to do is apply the proper quadrant rules on our reference angle in order to get those answers. And so let's see what we end up getting in quadrant 1. Remember, in quadrant 1, this is the nice thing, x is x prime. So the calculator, again, it's doing some service for us. So in this case, it actually gave us one of our solutions. So x actually is that 1.3181. All right, great. Now there is a secondary angle that also has that precise cosine ratio, and so that one is down in quadrant 4, and the way to get that one is to use what we got from the calculator and take it away from 2 pi. So that was our quadrant rule for quadrant 4, and let's go ahead and do 2 pi minus that answer. And whenever we kind of get that piece right here, I have it on my paper, so I'll go ahead and write that out. I get about 4.9651. And so 1 in quadrant 1, 1 in quadrant 4, and those are your 2 values on the primary interval. Now remember, there are an infinite number of solutions for this equation. So just keep adding 2 pi and subtracting 2 pi forever and ever on both those values, and you'll keep getting them, of course. Hey, before we wrap this on up here, again, good lesson. We'll definitely look at this more on the day 3 notes worksheet. So if you're struggling with it a little bit, that's all right. You'll see some more with me. But let's go ahead and just take a quick peek. So remember, I'm looking for the angles that have a cosine ratio of 1/4, or 0.25. And I said this is one of them up in quadrant 1. So let's see. Let's test it out. Cosine 1.3181 should be right around 0.25. And there it is, looking good. And then there's another one down in quadrant 4 that has that same cosine ratio. So cosine 4.9651, same thing, guys, should be right around 0.25. And so just from a unit circle perspective, here we go. That would be an x value of about 0.25 on your unit circle up here and down here. This is the one that's about 1.31 and change, and everybody, this is the one that's about 4.9, etc. and change. All right, great. This is looking perfect. So try some of these on your own if you get an opportunity. Until you get really good at this, put the 1, 2, 3 there. I think it's helpful. Find the reference angle, determine the 2 quadrants, and then set up the quadrant rules. All right, well, certainly thank you for listening. Ask questions if you have them, and definitely help each other out.